Hey, welcome! Today we are going way beyond the boring old number line to find some truly hidden geometry in the world of numbers. It all starts with one simple question that has this, well, surprisingly beautiful two-dimensional answer. All right, let's just dive right in. So it all kicks off with this little puzzle that, honestly, feels impossible at first. I mean, we all know the square root of 4 is 2, right? Because 2 times 2 is 4. Simple. But what number, when you multiply it by itself, gives you -1? If you try to figure this out on that classic number line we learned in school, you just hit a dead end. A positive number times itself is positive. A negative number times itself is also positive. So yeah, we're stuck. To find the answer, we literally have to think outside the line. So what did mathematicians do? Well, they got creative. They basically invented a solution. They called it I for the imaginary unit. But listen, this is not just some weird math trick. It is the key that unlocks a whole new dimension for numbers. By just deciding that I is the square root of -1, our question suddenly has an answer.
And with I in our back pocket, our little one-dimensional number line just explodes open into this huge two-dimensional world.
And this right here is the map of that world, the complex plane. The idea is actually super simple. We keep our old number line for the real numbers, 1, 2, 3, -5. That's our horizontal axis. But now we draw a new vertical axis for our imaginary numbers, all the multiples of I. And just like that, any number that looks like a plus di isn't just a number anymore. It's a location, a point on a map. Think of it like a coordinate. The A part tells you how many steps to take left or right, and the B part tells you how many steps to take up or down. So let's make this real. Say you want to find the number 3 plus 4i. You just start at 0, you go 3 units to the right along the real axis, and then you hang a left and go 4 units straight up. Bam! There it is. Every single complex number has its own unique address on this map. Okay, so we can plot these numbers. Now, this is where it gets really, really cool. All that boring arithmetic we learned, adding, multiplying, it's not just number crunching anymore. It becomes actual, visible movement on this map. Let's check out addition first. So you can picture each number as an arrow shooting out from the center to its point on the map. To add 2 of them together, you just stick one arrow onto the tip of the other. The result is just this simple, totally predictable slide across the plane. All right, addition is a nice, clean slide, but multiplication, what's going on there? If you multiply, say, 3 plus I by -2 plus 3i, you get 9 plus 7i. If you look at that on the map, it seems like a totally random leap. Is there some hidden pattern we're missing? Oh, you bet there is, and it is so elegant. This one little phrase right here captures the entire secret of what's happening. Add the angles and multiply the lengths. To really get it, though, we have to look at our numbers just a little bit differently. See, to unlock this pattern, we got to shift how we think. Instead of asking how far right and how far up, we need to start asking how far from the center and in what direction. That distance from the center, we call that r. And the direction, that's the angle, theta. This is the number's polar form, and it's the key to making multiplication make sense. So here it is, the big idea. When you multiply 2 complex numbers, you're literally performing a spin and stretch. You multiply their distances from the center, that's the stretch, and you add their angles together, that's the spin. It's a rotation and a scaling every single time. That jump that looked so random before, nope, it was a perfectly predictable spin and stretch. Okay, so addition and multiplication have this awesome geometry. But what about division? Now that's a trickier puzzle, but don't worry, it has an equally clever and beautiful solution. So the biggest headache with dividing complex numbers is that pesky little I in the denominator. I mean, how do you even divide by an imaginary number? Well, it turns out there's a trick so you don't have to. And for that, let me introduce you to the hero of this part of the story, the complex conjugate. It sounds fancy, but it's so simple. For any number a plus bi, its conjugate is just a minus bi. That's it. You just flip the sign on the imaginary part. And this image shows you exactly what's going on. The conjugate is just the number's perfect mirror image, reflected across that real horizontal axis. Same real part, but the imaginary part is flipped upside down. Okay, now here's the magic trick.
When you multiply any complex number by its conjugate, the imaginary bits perfectly cancel each other out, and what you're left with is always a purely real number. A squared plus b squared. No i's anywhere in sight. And that gives us a super simple 3-step recipe for division. First, you find the conjugate of the bottom number. Then you multiply both the top and the bottom of the fraction by it. You simplify, and voila! The denominator is now a plain old real number, and the problem is basically solved. So arithmetic makes these cool geometric shapes. But the truly mind-blowing patterns, they show up when we start looking at powers and roots. This is where the complex plane reveals its final and most beautiful secret. The master key that unlocks all of this is something called de Moivre's theorem, and it's really just a superpowered version of our spin and stretch rule. To raise a number to a power, you just raise its distance r to that power, and you multiply its angle theta by that power. So let's use this new superpower to answer a question that seems almost childishly simple. What are the cube roots of 8? Or, what number times itself again gives you 8? Well, duh, it's 2, right? 2 times 2 times 2 is 8. And on the real number line, that's it. That's the one and only answer. But, you know where I'm going with this, in the complex world, are there others? It turns out, using de Moivre's theorem, we find that there isn't just one cube root of 8. There are 3. We've got our good old friend 2, of course, but there are also these 2 other hidden complex roots, and they are every bit as much a cube root of 8 as the number 2 is. And now, for the grand finale, the incredible payoff. If we take those 3 roots and plot them on the complex plane, just look what happens. They form a perfect equilateral triangle, spaced out perfectly around the center. The answers aren't just random numbers, they form a beautiful, perfect geometric pattern. And this isn't just for 8, it happens for the roots of all numbers. So we started with a simple, almost impossible question about the square root of -1. And we ended up discovering this entire 2-dimensional universe where numbers have shape, direction, and stunning geometry. It really makes you wonder, doesn't it? What other beautiful patterns are still out there, just waiting to be found, hiding right beyond the edge of the number line?